To have Professor Max Welling here for giving the keynote lecture. Professor Dr. Max Welling is a full professor and research chair in machine learning at the University of Amsterdam and a Merkin Distinguished Visiting Professor at Caltech. He is co-founder and chief AI officer of the startup Cusp AI in materials design, and he is a fellow at the Canadian Institute for Advanced Research. He is also a fellow at the European Lab for Learning and Intelligent Systems, where he served on the founding board. His previous appointments include partner and VP at Microsoft Research, VP at Qualcomm Technologies, and professor at UC Irvine, postdoc at UCL and the University of Toronto, and a postdoc at Caltech. He finished his PhD in theoretical high-energy physics under supervision of Nobel laureate Professor Gerard Hooft. Max Welling has served as an associate director associate editor-in-chief of IEEE Transactions on Pattern Analysis and Machine Intelligence from 2011 to 2015. He serves on the advisory board of NeurIPS Foundation since 2015, and he is the co-founder of the European Lab for Learning and Intelligent Systems. He also served on the board of the European Lab for Learning and Intelligent Systems until 2021, and he has been program chair and general chair of NeurIPS in 2013 and 2014, respectively. Max Welling is also recipient of several awards, including the Kundering Prize in 2010 and the 10-year Test of Time Awards at ICML in 2021 and ICLR in 2024. Max, the floor is yours. We are looking forward to your talk.
Thank you. Thank you for that introduction. I realize I should shorten my bio a little bit. So. Yeah, it's a huge pleasure to be here. In fact, it's wonderful to see that there's a whole conference or a workshop dedicated to my favorite topic, free energy. So this title was there already before I started to work on this presentation, and it's very interesting that this is so well aligned. So what I'll be talking to you about today, I'll talk a bit about AI for science and the way I view there's a new scientific paradigm or a new paradigm for scientific discovery emerging. Then I'll talk about free energies and in physics and both in machine learning. I think these topics are, free energy emerges very naturally both in machine learning and in physics, of course. And then some examples, transition path sampling, classical density functional theory. If I have time, a quantum variational Monte Carlo, I'll not talk about gravitational lensing, and then an outlook. All right, free energy, my favorite topic. I'm sure I don't have to explain this to this audience because you're all about free energies, but I find there's an interesting analogy with sort of the disruptions that society went through. First, the Industrial Revolution, which you could think about as replacing manual work with machine work. And now we are in the middle of what you could call the sort of digital or information revolution, where we are replacing mental work with AI. And of course, that's the term that's connected to entropy, because entropy represents the amount of information we are not tracking in a particular system. And it was Steve Jobs who said, of all people, I'm not sure if he's a physicist or not, but he said this revolution, the information revolution, is a revolution of free energy as well, but of another kind. And he said it's free intellectual energy. And this is where that took us, the free intellectual energy. But as I will argue today, it's the actual free energy which is underlying these pictures. So it's not just free intellectual energy, it's actually, in a rather literal sense, free energy which has made these pictures possible. And of course, this has been now sort of gone to the domain of video with Sora. You've probably seen it all in the media. It's really interesting to look at these things and the progress that has been made. In particular, these dog images are infinitely entertaining. I can watch them for a long time. It's fantastic. But the question is this really where we want to put all our intellectual energy, our intellectual free energy, I would say? And to me, no. It's fun, but I'm very happy to say that these techniques which have been developed for these applications are actually being used today, and I'm sure many of you talk about that. These techniques are being used now in the sciences, where I get really excited. And of course, there's just the announcement of AlphaFold 2. We all know that you turn an amino acid sequence into a sort of three-dimensional structure, which is very important for the function of a protein. Here's a very interesting application of reinforcement learning to control a plasma inside a nuclear reactor. And this is some of our own work, and I'm sure this is being discussed here a lot as well. I already saw EGNN mentioned here, which is models that use equivariant neural networks to either predict properties or in the reverse setting actually generate molecules from noise. And this is an early work on that. Now, what is the paradigm shift that I think we are witnessing here? So there's two parts to that. So the first part is due to the increase in computation that we're witnessing, we are increasingly relying on in silico simulations rather than experiment, right? So in the old days, there was only experiment. You just tried things and you see what stuck, and then whatever worked, you iterated on. So later, of course, there was much more data-driven modeling. So you would do experiments and you would measure a lot of things about these experiments. And then based on that data analysis, you would then sort of do a next experiment. Where nowadays, we can even do pretty decent-sized simulations of molecules in a computer, right? And the reason that that's useful is that you can take away as much of the sort of the work that you want to do from the experiment to the computer, which is cheaper and much faster, or you can apply machine learning there. But of course, you always need the experiment in the end, right? In the end, you always have to go back to the lab and verify all the things that you've discovered in your computer. But there's a second part to this, which I think is perhaps more important, which is I call the from simulation to emulation. And I want to sort of illustrate that with this little cartoon here. So let's say you're a car manufacturer. I didn't get paid by Mercedes, by the way, but it's just accidental. So you design your first car, and you've already transitioned to the digital, the simulation-based sort of framework, and you do a wind tunnel experiment in your computer through simulation. Okay, so then, when the next car comes around, you would have to do it again. You would have to go again through the moves of doing this entire simulation, which is very expensive in your computer. But now the new paradigm shift is, instead of throwing away that data, is very valuable. So you recycle it. You store it in a big database, and then you recycle it into, you should train a neural network that tries to shortcut that simulation. So the more of these simulations you do, the more data you have available to train these models, the better they become. And the more often you can sort of shortcut these simulations. And this is a flywheel that accelerates, that goes faster and faster. Of course, there's many questions that people ask. Can you trust this model, right? It's one step further, from experiment to simulation to emulation. It's one step further from ground truth, if you wish. And so it's important that you add sort of uncertainty quantification to these models. And by the time, red flags turn on that this might not be a model that works well for this particular new molecule or new setting, you go back to the actual simulation, or you escalate all the way back to experiment if you don't trust your simulation as well. So I view that as this sort of the paradigm shift that we are witnessing, and also the popularity of machine learning in this field. Okay, so now I'll just go into a little bit more detail. So this is the most sort of equation-heavy slide for you. Well, actually, not quite sure, but anyway. So this is a equation-heavy slide for you. So I hope it's not too early for that. But so what I wanted to show you is this very deep connection between the free energy in the machine learning literature and the free energy in the chemistry or the physics literature. So I want to sort of point out there's these two. Let's go here. So most of you are probably chemists of some kind. So let's go here. So we have the free energy, which is defined as minus temperature times the log normalizing constant. That's the standard definition of a free energy in equilibrium. But you can bound that by a variational free energy, which also holds away from equilibrium. And that's given by the expectation of a Hamiltonian, the energy function, over any distribution really, that could be away from equilibrium, minus temperature times the entropy. So this is a very, very standard equation. And of course, we have P here, which is defined as the Boltzmann distribution, which is equilibrium distribution. So Z is sort of that Z that goes into there. Now, how does that look like in machine learning? Well, let's go through this derivation here. So we start off with the Boltzmann distribution, and then we write down the KL divergence between Q and P, Q being an arbitrary distribution and P this Boltzmann distribution. So you write it out, and you get an entropy term, you get an energy term, and you get the partition function. And if you reorganize that, you get the free energy, F minus log Z, so temperature is 1 here in this case, smaller than the variational free energy is the internal energy of the system out of equilibrium minus the entropy. So this is literally the free energy I wrote down in the first slide. And that you just derive by this very simple thing. Okay, now go to the machine learning side. In the machine learning, we write down things like this. Now, X is the data, the observations. So if you're a physicist, you could be observations, macroscopic observations about the system, maybe temperature, volume, whatever thing you measure here. So that's X. In machine learning, that's the data set. And you write down minus log P of X, which is the marginal likelihood, is upper bounded by minus the expected value over some variational posterior distribution over all the degrees of freedom, which we call latent degrees of freedom, which we're not tracking. So those are all the things that we have in our model, but we're not observing on. So those are the degrees of freedom of the molecule, all the vibrations and the motions of the atoms in the molecule, let's say. And then we have this log joint probability distribution, and then minus the entropy of this variational posterior distribution S. Now, if you compare these two, you'll see there's many analogies. We call this the evidence lower bound, or elbow, and that we can go through an exact same derivation, but now instead of writing the equilibrium distribution, we write this posterior distribution, P of Z given X, which is the object of interest. And we can develop that as, using Bayes' rule as Px given Z times Pz divided by Px. Now, if you go through exactly the same moves, you write down the KL, you get an entropy term, you get an energy term, which is now, identified as minus log Px given Z times Pz, and then there is this log partition function term. And then that means that minus log P of X is defined as the free energy and is upper bounded by the variational free energy, is like an energy term and an entropy term. So it's exactly the same. It's literally the same, except for that we have to identify this with an energy. And even you can map certain algorithms to concepts in physics, right? So there's this algorithm which minimizes this variational free energy as a matter of how do you learn. It's called EM, or variational EM, and it's super simple. Once you have this variational free energy, you first minimize it over Q, and then you minimize it over theta. So theta being the parameters in your Hamiltonian, or the parameters in your P, your generative model. You just keep iterating this until you converge. Well, if you look at thermodynamics, there is a similar relationship. The change in F is given by the change in the internal energy with respect to the parameters in your Hamiltonian, plus the change in the internal energy relative to the relaxation of your distribution Q, minus the change in the entropy given through the change in the distribution Q. And that you can identify as the first part is the work part, the second part is the heat part, and the third part is the system entropy change. So these two are actually equated to the total entropy change of the system, and that maps to the M step and the E step. So the M step is the change in work in order to minimize the free energy, and the E step is the change in the heat with the radiate, so the entropy of the external system and the entropy of the internal system, which is the E step. So there's a very beautiful alignment between these two theories. And in fact, if you dig a little deeper, there is this guy called Jaynes, E.T. Jaynes, who's been quite, involved in this. And his statement was maybe radical at that point. I think it's completely true. I don't think it's radical at all. He basically views statistical mechanics as Bayesian inference. So he literally makes this connection. He said these two things are the same. And he says that, for instance, the entropy in a physical system is nothing else as our ignorance about the system. So it's not something you can measure it indirectly, right? But it's not a quality, it's not an ontological state of a physical system, because the system is in one state only, if you look at it microscopically. But you can't look at it microscopically, you have to look at it macroscopically. So that your measurements are, not the positions of the actual molecule or atoms. And so whatever degrees of freedom we are missing out on when we do these macroscopic measurements, that's what the entropy term quantifies. So now I want to take the jump. So that sort of makes the case for me that these two things are at least extremely related. In my view, they're the same. One lives in a computer and the other one lives in the real world. And of course, Maxwell demons and stuff like that also, really study that. But how did this impact machine learning recently, right? And so there was this paper, which is kind of the first sort of start of diffusion-based models, which are now super popular and which produce all these beautiful videos and images. This is kind of the first paper I could track down. That was really sort of the first step. And it says, deep unsupervised learning using non-equilibrium thermodynamics. Also, these guys already, were deeply inspired by this connection when they wrote down this diffusion models, which is interesting because nowadays you don't see that anymore. And so how does that work? Well, you start with a sort of a data distribution like this. It's highly structured, so it's very low entropy. And then you start with a diffusion process, which increases the entropy, which is the natural way of the world, right? We increase the chaos in the world by sort of increasing the entropy. And then they study this process of going in this direction, and they learn to undo it. So they learn the dynamics to unscramble the egg, basically. That's what it does, right? So you start from noise, which is highly chaotic, and you've learned how to build an egg in your hand from an omelette. That's basically what this does, right? And so you can do that, of course, in a computer. And so later on, these models were, this is a 2021 paper, very influential paper, that further developed that by mapping it onto SDEs. So this is stochastic differential equation. It's Brownian motion with a drift term. And the drift term is linear typically. So you start with a data point and you start to diffuse it in this space of images, and in the end you always end up with some typical set thing, which is just some noisy image, a noisy looking image. And then they say, well, for this particular equation, we actually know how to invert it. It's known. You just have to add this extra term, which is the score function, which is the gradient of the log probability of the data distribution. The problem is you don't know this thing. And if you don't know it, well, what you do in physics, in machine learning, you train it from data. So they look at every step in this direction, and then they undo it in this direction, and they just fit a neural network to this thing. There's very interesting ways you can study processes like this in a sort of more physical way. You can write down fluctuation theorems. I'm not sure if you know about those, but it's basically relate the forward and the backward processes to each other. They say, how more likely is this than this when you just, let it run its course? That's related to the change, the total work done in this process, going from here to here, minus the change in the free energy. And this is actually a very important equation. If you take the average, called the Jarzynski equality, and that's a very important way to compute free energy differences. So the Jarzynski equality you can use to compute free energy differences, right? It's all related to this in ways. So you could imagine this paradigm actually to estimate free energy differences as a molecule is docking to a protein or something, right? Right. And so now I'll just talk a little bit, about some examples that we did in the lab. So here's these three guys, Emil Hogeboom, Victor Garcia Satores, and Clement Vignac, worked on this. So it's an equivariant model, which means we build in the symmetries when we generate, which only means if I take a molecule, I generate it in this configuration, or I generate it, somewhere else in a rotated configuration, it has exactly the same probability. It considers all of these different symmetry transformed molecules as one molecule, basically, as it should, right? And then, so this is how that looks like. So you start from noise, and you've trained it to work against the second law of thermodynamics to generate a highly structured object from noise. Okay, so so what can we conclude from this discussion? And sort of I've been teaching about this a little bit, and it's been an interesting journey for me as well. Free energy is really a very fundamental concept in machine learning, and it's not just diffusion models, which are here. Diffusion models, and then there is a sort of a version of that is sort of a deterministic version without noise, which we call normalizing flows. So these models are models to, machine learning models to generate images or generate things. These are called generative AI models. But it turns out that free energy, for instance, also I just sort of already alluded to this, variational inference and even MCMC sampling. You can all think of these things as versions of free energy minimization or of some kind, or a relaxation of a system. Like an MCMC chain is nothing else as sort of a system that through sampling it relaxes to its equilibrium state, which is the target distribution that you're interested in. And so there's inference and MCMC sampling, diffusion models, and machine learning. And then there's two other maybe more surprising ones where I'm not sure if you heard of Schrödinger bridges and optimal transport. This is the zero temperature limit of this one. It's basically if you start with one distribution and you want to sort of transport that to another distribution, and you want to do this optimally sort of fast or with the least amount of, I don't know, maybe work that you dissipate into the environment, so some optimal sense of moving that distribution to the other one. That's a Schrödinger bridge problem, and you can formulate that again as a free energy with two boundary constraints, one at the beginning and one at the end. And perhaps more surprisingly, optimal control you can also view as you can formulate it as a free energy problem. You can map the two to each other. It's very interesting, and I'll give you an example in a minute. So now I'll just go through a few examples that I've been working on with people from the lab. So the first one is an example of diffusion models. I guess this is the most relevant work here really for this audience. So this work was, I take some pocket, which is a sort of a protein pocket, and I want to generate a molecule, a ligand, let's say drug-like molecule inside that pocket. And I want to use these diffusion models to do that. But in addition, we also place certain anchors in there. So we say, we know this piece of a molecule would sit really well in this part of the pocket, so let me just put it there, right? And then we just ask the diffusion model, we train the diffusion model to complete this into something that looks like a molecule, a drug-like molecule. Now this is just the first step. It's called DiffLinker. It's just the first step. So these are the two guys at EPFL that did most of the work. It's worked together with Bruno Correira's group. And so these things don't look like drug molecules. If you know anything about this, you probably laugh at that. You say, well, that's not a drug-like molecule. And that's fine, right? This was the first paper. But as these things go, many, many papers follow up on this. And then, pretty soon, you can put in things like synthesizability, toxicity levels, whatever. You can put them in here and start generating more relevant molecules. So the second one is an example of something that is both a Schrödinger bridge problem and an optimal control problem. So we started from a Schrödinger bridge problem, and then we turned it into an optimal control problem because that's easier to solve. And so you might be familiar with this as well. It's very relevant for drug discovery, I think, which is called this transition path sampling. It's really trying to figure out what's the free energy difference between, let's say, one conformational state and another conformational state of a particular molecule. And the way I call this the Sisyphus project because there's this poor guy which has to roll up this rock, and then when it was somewhere up there, it would roll back down again forever. And so this is kind of the fate of a molecule sitting in a metastable state. It's sitting there, it's fluctuating around, but it needs to get over this free energy barrier or energy barrier to the other side. And if you just do this in a computer, it will never converge, right? It will basically forever sit there, and it will not actually fluctuate out of that well. But you can formulate this problem as a Schrödinger bridge problem now, right? You could say, well, there's one state, and this is where we start. There's another state, is where we need to end up. Now find for me the path which, let's say, maybe radiates out the least amount of heat in the process of doing that. So I'm going to guide it along the way. I'm going to add forces, but I want to do it in such a way that it goes over sort of this lowest free energy barrier path. It shouldn't go all the way here because that's not very physical. So it needs to fluctuate over that lowest part of the sort of the hill. And you can do that by basically thinking about, I want to minimize the amount of heat dissipation or work dissipated work when I do that. So you can sort of, first of all, write the dynamics of the system as usual, as Langevin dynamics. It's a molecule in a heat bath. The change in the position is given by the velocity. The change in the velocity is given by a force, which is the natural force of the molecules, plus a noise term, which is the collisions with the environment and the heat bath. And now here's this external force, which is a force I'm adding in my computer, right? And this is the policy of a reinforcement learning problem or control problem. So it's a controlled force that I can optimize that drives this molecule from this part to this part. And basically this is, we started using methods from control theory in order to find these paths. And the nice thing is that when you normally do these things, when the chemists do these things, they have to first define reaction coordinates. Because if you define a reaction coordinate, you can map everything down to a 1 or 2 dimensional space, whatever low dimensional space, and then you can, the thing becomes far more tractable. So here we do it in the full dimensional space. We give a little force to every atom in the molecule, and we just optimize that policy. So we don't have to make these choices up front. And here you see, we did many experiments, but here you see an example of a free energy surface. The molecule is moving, and we're just forcing it to go over sort of this barrier here to get to the other metastable state. And here we track sort of the free energy as that happens. And here you see the conformation of the molecule moving around. This was work with Lars Holdijk and a whole bunch of other collaborators. Okay, and then the third part, I could have filled all the things here because there's many cool examples of where free energy really is the core way to formulate these problems. But the last part is something I did recently. I'm very excited about with a student, Jacco Dijkman. So this is now basically a physics project. It's called classical density functional theory. I'm not sure if you've heard of it. Jacobus Dijkman. He was actually in this field before he started the PhD with me, but he was, I think, working at Janssen or something. So this is this interesting technique called classical DFTs. You probably all have heard of density functional theory, but then you think about quantum density functional theory. This is nothing to do, well, it's the same idea, but it's completely thermodynamics. So it doesn't do any quantum stuff here. So what happens is that you just write down the grand canonical partition function, or grand canonical function, I guess functional of the density. So this is a density of particles in 3 dimensions. So it counts the number of particles that are sitting in the particular position. And you can sort of split this up into a few terms. There's the first term, which is the internal free energy. So this is how the different molecules inside your gas or your liquid are interacting with each other. So this is not a theory of individual particles. This is a sort of a continuum limit, where you think of this as sort of a field, a continuous field of particle densities. And then there is an interaction term where the liquid, let's say, interacts with the external forces, which could be, let's say, a protein or something like this, or another molecule that the liquid or the gas interacts with. And then there's the chemical potential here. And so now what we're going to do is, so these parts are very clear, right? We know what this V is. We are going to optimize this density, so that's all fine. It's this thing here which is complicated. It determines the viscosity of this liquid, and it determines the properties of the particular liquid that you're looking at. And physicists have been writing down terms for that. So they say, okay, let's think very hard about what that should look like, and just write long equations about what that thing should look like for a particular molecule. But this method didn't become very popular because these approximations are actually quite poor. It's very hard to make this work, turns out. So this is a perfect case for machine learning, because we know how to do molecular dynamic simulations for problems like this, right? We can actually simulate them with molecular dynamics. And then we can train a machine learning neural network to represent this F for us. And so instead of a short equation with a few parameters, we can now write down a neural network with, 100 million parameters and see how that fares, right? So that's what we did. So so let's say first, so we learned this F of rho from MD data, and then once all of that is done, now all these terms are here. I can now change the external potential V, and then minimize this thing over rho. And that basically gives you an equation like this. This would be the physical way in which the system equilibrates. This is just a Fokker-Planck-like equation. But anyway, at the equilibrium state of this system, you then have the equilibrium distribution like this, for a new external potential. And so here's a little bit more detail. So the setup. So you say you start with a bunch of MD simulations, and for a particular potential, you get some equilibrium density profile. So you write down, like you discretize it, and you write down all the densities, for each one of the grid points. Then there is this equation, which happens to be true, which you can then use to turn your density profile of your MD simulation into this first derivative of the free energy. And this needs to hold at equilibrium. So this gives you now ground truth for the functional derivative of the free energy, the internal free energy, let's say, with respect to the density. You can also write down a neural network. So there's a neural network that takes in the input densities, push them through a CNN, and now you predict the free energy. And then you do auto differentiation to get all the functional derivatives, df, d rho. And now you have the ground truth, and you have the predicted one, and then you write down a cost function that tries to bring those two things together by changing the parameters of this neural network. That's all there is to it. Once you have done the whole thing, when the whole thing is finished, you can then say, okay, for a new external potential, I can now use the same equation but rewritten. I stick in this new external potential. I have this object because that's my neural net. And now iterate this process to get to a new equilibrium distribution. So let's see if I can. Let me just show maybe an example of this. Okay, so here's a nice example of this. So it goes very quickly because it converges crazy fast. So this is a one-dimensional example. We're now working on more examples like that. So here you see the iterations of some of these density profiles where, so the row of this blue line is basically the solution which iterates itself to the ground truth density profile. Okay, so what I wanted to say is that there's actually a much better method for this. What we are now doing is sort of almost like magic. What we do is we never give it any external potentials when we train this method. Because it's actually quite annoying, because you have to sample the whole space of all these external potentials in order to cover the space in which this model is trained. But there is a way in which you train the system completely with zero potential. So that means that the liquid is uniform, it's just bulk, and you do these simulations, but there's fluctuations anyway. When you sample this thing, there's small little fluctuations going on. What you can do is you can basically look in your MD simulations and you can extract this radial distribution function, which tells you, if you, in any point in any direction, you move radially out. So what happens to the density of the molecules? And of course, in the beginning, there can be nothing because this actually molecule has finite size, and you cannot put something that overlaps with it. So there's 0, and then it shoots up because the next molecule then connects to it. And from that, you can compute the second order derivative. So this is the correlation function over rho I and rho j of this free energy. And now you can go the same trick. You can take, you take your input distribution from your MD simulations, you push it, through the CNN to get the free energy, and then you do auto differentiation twice in order to get the correlation function, and then you match these two together, and you train. And then once you now need to test this, now for the first time, you change the external potential, and then you go through the same thing. So you stick in your row, you predict the free energy, do auto differentiation once, and you stick it in this equation. Now with the new potential, it's never seen this potential before, with this trained neural network, and you iterate this, and then you see if this thing works. So it feels to me like magic, and we've been discussing this with the inventor of this, Bob Evans, and the best thing we come up with is actually there is a lot of information in this thing, which is actually a large perturbation to the problem. You can see it because this, you're pushing out things, and you sort of these correlations have a lot of information in them. All right, so already sort of showed this one, I guess, and this one. Oh, here's another one. And here's a whole bunch of sort of, we did a whole series of these tests. The paper is, by the way, out on archive if you want to read about it. But sort of these are density profiles which are pretty extreme. And again, it's not trained on any, so this method here, the blue method, is not trained on any external potentials, and the red method is. And you see it, and the dotted line is the MCMC sample, or the MD, these are the MD simulations. And it tracks these things very well. And so these lines here are sort of the state-of-the-art methods that the physicist would write down before, right? So these are written, actual equations you write down for this internal free energy, and then you run this, and you see it just doesn't work very well. But with these neural networks, it works really well. So I find this a very interesting application where machine learning can really make a large impact. Now, I did have something on quantum. I'm just going to be extremely short about this because I don't know, it's getting a little technical, and I'm sure everybody wants to hear this at this stage. But let me just set the scene. So the scene is that there's a very important method called quantum variational Monte Carlo. And what you do is you now train a neural network to predict the wave function of the ground state. So you stick in a configuration of a molecule or an atom or whatever. So it's the positions of the particular atoms of a molecule, and then you're interested in predicting sort of the electronic structure that's represented by a wave function. So you push these things through a neural network, and the neural network then actually predicts the wave function coefficients, and from there you can then minimize that in order to get to the ground state energy. And this is a nice visualization from DeepMind. They had a model called FermiNet. This is a model called PauliNet. Here you sort of see these points are sort of the electrons as they are simulated by this system. Okay, so I'm not gonna do this because there's a lot of equations, and I sense the audience, it may not be what we want to hear right now. So I am going to talk about this for a little bit. So now that we've seen a whole bunch of ways in which machine learning and physics and chemistry connect, I think at a very deep level through the free energy formulation. So we've seen how ideas from physics impact machine learning. Diffusion models are really an example of insights from physics put in at work in a machine learning model. But we can also, of course, do the opposite. Now, I've shown you a few applications of that. How can we use machine learning to improve methods in the sciences? And this can happen at the sort of quantum level. So here's the time-dependent Schrödinger equation. There's now being methods developed that, like the classical DFT, also for the quantum DFT, you can learn this functional using a neural network, and you can vastly accelerate the quantum DFT methods. And then I also briefly talked about this Fermi and PauliNet, this quantum variational Monte Carlo, where we can accelerate the neural network training for the wave function and the ground state. Now, if you go one level up, you go to molecular simulation, which is, I'm sure, very relevant for this group. This is now so this is a PDE. This is now a stochastic differential equation, where the one it's similar to the one I already showed you, which is the change in position is given by the velocity, and the change of velocity is given by a force plus a friction term plus a collision term, a noise term. And now there's been a huge amount of work in replacing this quantity, which is the force, which you really have to compute by DFT. Quantum DFT is very hard to compute that if you want to do it right. But people have built training sets, like in this new emulation paradigm I showed. They've built large training sets and then trained neural networks to replace this term by what's called a machine-learned force field. And then you can accelerate molecular dynamics tremendously by replacing the quantum DFT calculation by a force field. And these equivariant graph neural networks and all have been used to do this. The top performers right now, I think, are MACE and Equiformer, both equivariant neural networks. So this is what I just talked about. This is a classical DFT, which is a method you can also accept. It's similar to here to quantum DFT. You can train these free energy functionals, and then at even a higher level, so being involved at Microsoft at work to model sort of weather prediction using very large neural networks. There's a lot of data in that field, and so instead of trying to stay close to the physics, this takes the approach of just train a map to directly predict the weather of the next day. So it's a huge transformer-based model that takes the state of all the weather variables at this time and try to predict the state of all the weather variables at a future time just through one massive neural network. And that's because there's so much data, it's been able to predict as well as just solving the Navier-Stokes equations. And in the beginning, I've worked a bit with meteorology offices on this. In the beginning, people were very skeptical about this. It's like you will not replace something that is like 100 years of work on numerically solving these methods. But it turns out these methods are about as accurate and 10,000 times faster than actually solving them numerically. And so it really has caught the attention now of meteorologists, like the UK Met Office is really investing now in trying to understand it and thinking about how to integrate these what we call surrogate models into their pipeline. So you probably want to make sure you have at least one or two numerical predictors in there in your sort of ensemble, but have a lot of these neural network predictors in there as well. And then there's beautiful applications, of course. The ones that I'm mostly excited about is drug discovery, catalysis, and in material science, sort of generating or designing new materials using machine learning methods. Yeah, and then so this I would say is an overview of where I think this field is going. So more generally, so we have very mature molecular science fields like condensed matter physics, computational chemistry, and molecular biology that are starting to use techniques and rely more on computational sciences like supercomputing, machine learning, sort of more recently, and hopefully in the future also quantum computing increasingly. And there's a large pool from applications in sustainability, maybe carbon capture is very interesting here, or energy transition, hydrogen production, or health, which is designing new drugs, as you do here, right? And I find it fascinating that we have named our ages in which humanity live after the materials that we are using, and I think there might be an age where we can really design materials on demand. In the same way that you type a query in a sort of a Google box, I want information of a particular kind. At some point you might actually type a query, I want a material with these properties in a query box, and you might get a number of candidates that have those properties. And this is actually the work of the startup that I just started, CASP AI, is developing a new MOF structures, metal organic frameworks for carbon capture. Okay, so last slide. So again, free energy is my favorite topic because it bridges so beautifully the sciences and machine learning. And I think a lot of new and interesting ideas will come from this interface. If you're interested, stochastic thermodynamics is a really beautiful field of non-equilibrium thermodynamics where you can really map both of these things onto. In the meantime, it's very useful because machine learning models are creating lots of new hammers and new tools for the chemist and the medicinal chemist to use, and there will be many more of those in the future based on generative AI, but also property predictors. And there's beautiful applications in health and sustainability, for instance, for new drugs and designing new materials. And I'll stop there, and then feel free to ask questions.
Thank you, Max, for a great talk. So we can have a few questions right now. No? Okay.
Hello, Max. You'll remember me. We met when you were working at Microsoft Research in Cambridge. There are lots of things that you're saying that I would like to talk to you about, and I'm not going to ask you much about them now. One of the problems with this area is there's so much hype behind it, and it's not flaky hype, it's backed by a lot of corporations who have tremendous influence. You mentioned healthcare. We're in an area which is to do with healthcare. Let me just give you an example of something that occurred on the 11th of March 2023 in the UK. A group of independent experts reported to the NHS on how AI systems are performing inside the National Health Service. And the reading of that is pretty shocking because it actually reveals what we'd expect from a system that's based on statistical inference. In other words, we get a data set and we use that to infer how we're going to treat the next patient. Those data sets are overwhelmingly actually white and male still today. So it's completely misassigning what it should be doing to the patients. So the answer to that is presumably we just try to create more data sets, bigger ones that are more diverse. So the problem ultimately, though, is this, because we're trying to treat patients on an equal footing, personally, independent of race, creed, religion, gender. And what we're actually doing with these techniques is predicting, let's say, your health on the basis of lots of other people's.
Yeah, I understand.
Can't we do better than that?
Yeah, so that's a great question. Of course, many initiatives in responsible AI and all that are exactly about this problem. My response to this is, this is perhaps a naive way of applying these techniques for very important problems, and things like this have gone very wrong in the Netherlands as well, when algorithms were used to, chase people whether they would predict their tax, whether they would pay their tax or not. But the interesting part, I think, is that if you think about this long run, so the first thing to say is that humans have these biases as well. There's many recorded instances that people from prison, if they want to, if they apply for probation and they face a jury before lunch or after lunch, they get a different outcome, because before lunch people are grumpy and they're hungry, and after lunch they're happy and their stomach is filled. So we are full of these biases. In fact, there's also many of them when you can sort of, even though you might not think you're racist to some degree, if you do these tests, you figure out that you do have a different attitude when you have to very quickly respond to something with a different skin color. It's pretty disturbing, actually. So I believe humans are filled with these. But here is an opportunity to actually iron them out using machine learning and proper statistical techniques. So there's ways in which you can actually make sure in your algorithm, if you know the sort of the features that you do not want to discriminate on, you can make sure that the algorithm doesn't see them in any way, not even correlations to those features. So there's this debiasing and de-discrimination methods that have been developed already. They're more sophisticated than just a naive sort of application of your technique, and that's, I think, where the problem is. It's in the hands of people who don't really understand what they're doing. They're not aware of these risks that are behind it. So there should just be a lot of people educated in these more responsible AI techniques so that these methods get applied in the right way. I think, so in the short term, yes, I think this is a real problem, but I also see that it could actually overcome a problem that's already with us, because we humans also have these biases in them. I hope that sort of works for you, but let's talk more.
We have time for one more short question.
Okay, sure. Thanks for this broad overview of different approaches connecting free energy and AI approaches. The diffusion model, so the generative diffusion model-based approaches to de novo design new molecules, at least some of the cases that I've seen, they seem to be hampered not only by sort of topology or sort of the chemistry not being just right, but also geometry of molecules being generated not being just. Have you sort of systematically analyzed the molecules that you generated? I saw the example of the thiophene and the amide, and you might sort of think it would be the other way around, with sort of force field or experimental structures. And what are your experiences there? So
Personally, I work with other people that do these things rather than me. So this was done in Bruno Correira's lab, for instance. So we do do simple checks, like we check whether, let's say, the molecule is an actual thermodynamically stable object that doesn't explode when you sort of let it go. But these are quite naive metrics, and I'm completely with you that. So these are the first steps. So one thing you could do is, once you generate something, to do at least a few, just equilibrate the system using, an MD simulation to at least make sure that this thing that is at some equilibrium state of a proper MD simulation. That's the first thing. But the other thing which is really bad about that particular example is that it didn't have as a metric to optimize any things that you guys care about, right? You care about, this is actually something that I need to be able to synthesize or something like this. Or I know a few things that I really do not want in this molecule, and then they show up because it's never told that that's bad. So I think the solution to this is to come up with much better metrics and then incorporate those metrics in the generation process. And in fact, you can do that. There's guided diffusion, which basically takes a random sample and moves it into a direction where these properties, that you like under your metric are actually score high. Now, this is a process. The way I view this is, these are the first steps. So you can sort of trust that by a lot of work, these things improve over time. There is a lot of work to do. Or you could reject them and say, our old methods are better. And so, I've seen that happen a few times. And sometimes it's correct, I would say. Sometimes this feedback, this critical feedback is very valuable and very true. In machine learning, we tend to get overexcited about things. And I would even say arrogant about things. And it's really putting together teams of domain experts of a particular field, plus the machine learning each other's language, and generating the right stuff, which I think is the right approach.
Okay, we have time for one last question.
Thank you so much for such a nice talk. I was wondering, since I have a question regarding the classical DFT, and also since we've finished talking about materials, if I understand correctly, you've mainly worked on the classical DFT with liquids, but I was wondering whether you think there's any purpose or any applicability on maybe applying this to polymers, because sometimes polymers are extremely hard to parameterize, and they're also very trendy as new materials. And then when you go on to more complicated polymers, like conjugated polymers, it's very hard. So a method like that, I think, would be
So this is a great question, and I'm not a chemist, but I did talk to Hans Fraaije. I'm not sure if he's here or not. He's right there. And he explained to me, so you should talk to him, but he explained to me how methods that are very, very similar to classical DFT actually have already been successfully applied to polymers. So right there, so for the break, make sure you talk to Hans.
Yeah, sure, thank you.
Okay, so let's thank Max one last time for his great talk. And then it is time for the coffee break. We will reconvene here at 10:30, I think.